An electric motor is an electromechanical device that converts electrical energy into mechanical energy. Electric motors can be divided into two different categories, DC motor and AC motor. DC motors are powered by direct current, whereas AC motors are powered by alternating current. Examples of DC motors include brush and brushless, and synchronous and induction motors are examples of AC motor. The fundamental driving force behind all electric motors, whether they are AC or DC, is magnetism. Magnetic fields are formed in both the rotor and the stator. Rotor is the rotating part of the motor, stator is the stationary part of the motor. The product between these two fields gives rise to a force and thus a torque on the motor shaft. One or both of these fields must be made to change with the rotation of the motor. This is done by either switching the poles on and off at the right time or by varying the strength of the pole. So pole basically means the strength of the magnetic field. So let's look at some basic parts of an electric motor. A motor uses magnets to create motion. Opposites attract and likes repel. Inside an electric motor, these attracting and repelling forces create rotational motion. In the above diagram, you can see two magnets. One is the north and the other one is the south. And then we have the armature or the rotor, which is an electromagnet, while the field magnets are permanent magnets. So these are your permanent magnets or your field magnets, and this is your rotor, the rotating part, and these coils, once the current passes through them, becomes a electromagnet. So let's look at the basic operating principle. An electric current in a magnetic field will experience a force. If the current carrying wire is bent into a loop, then the two sides of the loop which are at right angles to the magnetic field will experience forces but in opposite directions. The pair of forces creates a turning influence or torque to rotate the coil. So in a practical motor will have multiple coils which will be wounded onto the rotor, and by having increased number of coils it ensures that the motor or the rotor rotates smoothly. So let's just look at a brief intro into what an electromagnet is. In its simplest form, it consists of an iron bar wrapped in a coil of wire. On its own, it does nothing. However, if you pass an electric current through the wire, a magnetic field is formed in the iron bar and it becomes magnetic in nature. Let's look at DC motors. A DC motor is powered by direct current. Every DC motor has these 6 basic parts. It has an axle, rotor which is called the armature, the stator which is the stationary part, commutator, field magnets and the brushes. So these are your field magnets shown in green and red. This is the rotor over here, which is the rotating part of the motor. You've got coils which are wound on the rotor itself. You've got the axle, you've got the commutator, and then finally the brush. The basic DC motor has 2 windings and 2 permanent magnets as shown in the diagram here. You've got the north pole, you've got the south pole, you've got the rotor which has 2 coils. The coils are powered from the commutator and the brush. So power is supplied to the coils through the commutator and the brushes. During a full cycle of the rotor, the current that runs through each winding changes direction once. Moreover, the windings of the 2 magnets are winded in the reversed direction. Brushed DC motors. This kind of DC motor is called brushed DC motor because it uses brushes. So these brushes are used to supply current to the coil. The brushes provide the coil with power. The brushes are metallic pieces that are pushed against the commutator. The commutator is simply a metallic ring which is also conductive in nature, but it is divided into 2. So with the help of the brush and the commutator, current is supplied to the coils which are on the rotor. So the commutator is fixed to the shaft of the motor. Each semi-ring has 1 pole of each coil attached to it. Changes in the electric poles has an effect on the magnetic poles. So as a result, you'll see this in figure. So let's assume this is your north pole and this is your south pole in blue. So you'll see that as the commutator rotates, the poles switch. So north becomes north over here, and then this south pole as it approaches this becomes north pole once more, and it ensures that the rotor rotates in the same direction. So this is a very typical example of brushed DC motors. So this motor you will find in toys, and I hope you would have come across this. So this is the inside part of the DC motor. You can see the coils wound onto the rotor. You can see the stator. You can see the field magnets. In this case, these field magnets are permanent magnets. Moving on, we have IC motors. An IC motor is powered from alternating current. Mostly it consists of two basic parts: outside stationary rotor having coils supplied with IC to produce the rotating magnetic field. So we'll look at two types of motors in this section. One will be synchronous and the other one will be induction. So you will learn that in both of these motors, the stationary stator is always supplied with IC current to produce the rotating magnetic field. Now what we have is inside rotor that is given a torque by the rotating field. Now what happens is, since the current is alternating, the motor will run smoothly only at the frequency of a sine wave. As mentioned earlier, two types of IC motors, synchronous and induction. So this is few examples of induction motors. So let's look at the operating principle of an induction motor. In an induction motor, what we have is, we have electric current induced in the rotating coils rather than supplied to them directly. So in induction motor, IC current is supplied to the stator and rotating magnetic field is created. However, in the rotor, we don't supply current, but what happens is current is induced into the rotor coils. So induction motor runs slightly lower than the supply frequency. Magnetic field on the rotor is created by an induced current. So let's look at the operating principle of these induction motors. The IC power supplied to the stator creates a magnetic field that rotates in time with the IC oscillations, and this is supplied to the stationary part of the motor, the stator. The rotating magnetic field then induces an opposing current in the induction motor's rotor, which is the secondary winding. Now what happens is, these currents in turn create magnetic fields in the rotor. The cause of the induced current in the rotor is the rotating stator magnetic field. So what this sentence tries to tell you is that just because on the stator we've got a rotating magnetic field, this rotating magnetic field induces the current on the windings of the rotor. The rotor will then start to rotate in the direction of the rotating magnetic field. Here we have examples of induction motor, and one of the most common type of induction motor is a squirrel cage induction motor. However, we've got many different types of induction motors. The next type of motor is synchronous motor, and in a synchronous motor again IC current is supplied to the stator, which is the stationary part, or basically the field windings. So IC current is supplied to it, and this causes a rotating magnetic field. The stator winding creates a rotating magnetic field. The rotor locks in with the rotating magnetic field and rotates along with it. Once the rotor locks in with the rotating magnetic field, the motor is said to be in synchronization. The only difference in a synchronous motor compared to induction motor is that, looking at the coils that are on the rotor, in induction motor current is induced into the coils of the rotor. However, for synchronous motor, DC current is supplied to the coils of the rotor. So that's the fundamental difference between an induction and a synchronous motor. So what we have here is few examples of synchronous motor. You can see the windings, you can see the rotor, and this is the entire setup of a synchronous motor. For synchronous motor, we have something which is called the synchronous speed. In a motor, synchronous speed is the speed at which the magnetic field rotates. Depending on the motor design, the actual mechanical speed may be equivalent or slightly smaller. So when that mechanical speed is equivalent, it is the synchronous motor, and if it is slightly smaller, it's a asynchronous motor. The synchronous speed depends on two things. One is the electrical frequency F, which normally ranges between 50 to 60 Hz, and then the number of poles and that the motor has. The formula for calculating synchronous speed is simply given as your synchronous speed, which is denoted as capital N, is equals to 120 times F divided by small n. F is the frequency and small n is the number of poles that a motor has. Now what we have is this just simply shows a comparison between an induction motor and a synchronous motor. So I'll just look at just one. So the first point, for induction motor, it does not need DC excitation and is singly excited machine. So what this means is that the rotor of the induction motor does not require DC current, but the current is induced into the rotor. Whereas for synchronous motor, it's a doubly fed excited machine. So what it means is it requires both DC and AC currents. Induction motors, it possesses inherent starting torque, whereas for synchronous motor, it requires external means for starting. So there are a couple of differences as mentioned in this table. So you're required to know a couple of them. Now what we have is we have uses of the two different types of motors that we're talking about. So we've got brushed DC, brushless DC, and we've got AC motors, synchronous as induction. So you can see different applications of these motors. Applications of electric motors can be for something which is very, very small. At the same time, motors can be used for large applications as well.